Hey, Dr. Godes. Who's the new guy?
That's actually our old friend, R, the ideal gas constant.
So why are we seeing this instead?
Well, so the number is different, 8.314, but that's because the units are different, right? We're going to use the ideal gas constant in a different context, and so we are changing the units, and so the numerical value changes. It turns out that if you go through all the unit conversions, this is exactly the same as our old units of R.
Okay, so we're heading into energy? Is that what this
Yeah,
pre-class
exactly.
video?
So welcome to the pre-class video on kinetic and molecular theory. So we're going to try to understand how the gas laws come out of fundamentally how gases behave.
Okay.
And so the idea is that gases are just small particles that are kind of moving around randomly, right?
Okay.
They're running into each other, they're running into the walls, and what causes things like pressure is the force of molecules hitting the wall.
Okay.
Okay? So one of the things we're going to have to understand are these graphs called probability distributions. And it's kind of a hard concept, and so Tyler and I thought that we could go through an example.
Sure.
And the example we wanted to talk about was running a marathon race, right? You got this, the New York Marathon. Thousands of people in this race, right? Some of them are going fast, some of them are going slow. A lot of them are kind of in the middle, right? And so the idea is, well, we can graph the probability of a certain time or how fast somebody is running. And so on this axis, let's say that it is time. How long it takes to complete the race.
Sure.
And every minute, we're going to measure how many people cross the finish line in a given time interval.
Okay.
Right? And so, of course, as we start going along the race, nobody's crossing the finish line. Right? And so there's basically 0 crossing the finish line. And this axis is going to be number of people.
Okay. Poople.
Poople. Hard to spell sideways, hard to spell period, right? And so the first person crosses the line, and in the New York Marathon that was just run, it was a single person, and so, boop, it bumps up. And then maybe a little while later, a couple more come in. Well, in that next time interval, maybe it goes up a little bit. And then as time goes on, more people come in any given time interval, right? And so more people come in, and more people come in, and more people come in, and more people come in. And then it gets up to kind of a peak. And then we measure more.
Right.
Well, not as many, most of the people have finished, right?
Right.
Not as many people are coming in. Not as many people. And it kind of drops off, right? And so each slice of time, you get this distribution. Some are coming in very low times, i.e. the fast ones.
Right.
Who's coming in here?
Grandma.
Grandma, me. I'm coming in down here,
Yeah, me too.
really slow. But a lot of people kind of in the middle, kind of average, right? And so if I were to ask, well, what's the average time that people come in, complete this marathon in, where would you pick on this graph?
Well, I'd probably pick, where the peak is, because that's when most of the people are coming in, and once you see it start to tail off, that means most of the people have already finished.
Exactly. And maybe about as many people went faster than that, and about as many people went slower. Turns out it's not exactly in the middle because it's what's called a skewed distribution. But if you were to guess, it's somewhere around the peak. That's going to be the average speed. And that's going to be the most likely speed for a molecule. Some are going to be a molecule. Oh, I forgot the analogy. A person. Some are going to be faster, some are going to be slower, and there's just a random distribution.
And most of them are somewhere here in the middle, running an average.
Exactly. And as a matter of fact, if you were to measure speeds in the middle of the race, people don't run at constant speed either. They speed up, they slow down. Well, molecules do. They don't just speed up and slow down. They speed up and slow down because they run into something. They run into something and transfer the momentum.
Right.
One goes off faster, one goes off slower.
Right. Hopefully that's not happening with the marathon runners.
Hopefully that's not, except at the very beginning.
Yeah.
Okay. So hopefully this is enough information to help you get started on the activity. keep track of units when you're doing calculations, and then keep in mind this distribution graph.
All right, good luck.
Good luck.